Thank you. So here's the joint work with Zhan Fei Yeo from the NTU. So let me just begin this talk with this forward eikonal equation. So this is the hand. This is the hand here.
Yes, we see that.
Okay.
Yeah.
All right. But yeah. So this is the forward eikonal equation. So as you see on the right-hand side here, we have the slowness function s. So when this s is known, we can solve this equation. So x0 here is the source point, and we suppose that we have the Zollner boundary condition here. So if this right-hand side is known, we can solve this equation. And the solution of this equation, this figure T here, is the time it takes for a wave from this point, this source point here, to reach this point x. So if you know this slowness function on the right-hand side, then you can solve the forward equation to find the solution T. So the aim of my talk is that suppose that we have some partial information on the solution T of the forward equation. We want to go back to determine the right-hand side. Here what you see is that the slowness here depends on this little u. So what this little u is and how this s depends on u, I will talk more on that. So we suppose suppose that this forward map G here, that is a vector in Rn. So that is the solution of the forward eikonal equation at the points x1, so on, x1, x2, so on, xn inside the domain D. So this forward map is known with the noise. So this nu here is a noise, and we suppose that this noise follows a Gaussian distribution in Rn. So the covariance of the noise is the Wiggin sigma here. Now, because the right-hand side S here depends on this little u, so the solution of the forward equation also depends on this little u. So that is why the forward map GU here also depends on u. So that is why I've got G as the u. And the delta, that is the summation of the forward map GU and this noise. And our aim is to find the S here given the delta, and finding this s x u and finding u are just exactly the same. So when we can find this little u, we can find this x. So here in this talk, we follow the Bayesian framework. So we assume that this little u that we wish to find, it belongs to a prior probability space. So that is this big U that you see here. And we assume the log normal form for this S. So here's the form of S. So it's this function as a star. And then we've got e raised to the sum. So I've got this function as bar, and the sum when this I goes from 1 to infinity of ui times ci. Now, so the functions s star here, and the s bar and the ci, all of them are known, so they are in the L infinity d. And s star here, we have it here, but we do not need to have it here. So we just assume that it is just a non-negative function. And the ui, we suppose that we follow the normal distribution, as you see here. So ui follows the normal distribution, and the little u that the slowness s depends on, that is the u1, u2, so on in the in Rn. So by this Rn here, what I mean is that the u1 is in R, u2 is in R, and so on. Now, so the big U, the big U that you see here, we define it as the set of all of those E1, E2, and so on, such that the summation for the absolute value of UI times this BI is finite. And BI, it is just the L infinity norm of the function CI. And here we suppose that the summation for all of this BI when I go from 1 to infinity is finite. So the big U, that is set of all this U1, U2, and so on, such that the sum of the absolute value of UI times BI is finite. BI, that is just this strict norm of this C and I. Now, because we defined this big U like here, so we just define the sigma algebra, this theta here, as the restriction of the tensor product of the modal sigma algebra on R to the set U and the prior probability, this gamma, that is the restriction of the tensor product of the normal probability to the set U. So because this condition is the summation of all of this BI is finite, so we can show that the gamma U here is 1. So the prior probability space, this big U, it is defined here, and the gamma, it is defined as the restriction of the tensor product of the normal distribution to this U, and gamma U here is 1. So my aim here is to determine the slowness is SXU here, and the delta here is known. So that means that we need to find U inside this big U. So I will follow the Bayesian framework. So we determine the posterior, that is the conditional probability of U given this delta, that is this gamma delta here that you see here. And from the Bayes rule, this is what we have. On the right-hand side, we have the conditional probability of delta when U is known. So we can write down the density function of this the likelihood on the right-hand side. That is because if you look at how we define this delta here, so that is a summation of this du and the noise nu, which follows the Gaussian distribution and the covariance and sigma here. So if the GU here is known, then this delta follows the Gaussian distribution in Rn. It's the mean value GU and the covariance and sigma. So that is why we can write down the density function of the conditional probability of delta when this U is known. So this is the density function. So that is the latency times e raised to the power minus phi U delta, and this phi U delta is the well-known mismatch function, which is defined here. That is the sigma norm in Rn of the difference between the forward map GU and what we see, that is this delta, so the sigma norm in Rn square, and that's 1/2 here. So from here we can write the Radon-Nikodym derivative of the posterior and prior. So this is what we have. So I have d gamma delta, but d gamma is proportional to e raised to this minus phi U delta. But here we are dealing with an infinite dimensional probability space. So we need to make sure that the Bayes rule that we have here holds, and we need to make sure that we can write the Radon-Nikodym derivative of the posterior and the prior is the form that you see here. So in order to make sure that we can, to make sure that the Bayes rule holds, we need to show that the forward map D that you see here, that's a map from probability space U to Rn. We need to make sure that this forward map is measurable. That is in the paper by Cotter and so on in 2009. In order to show that this map is measurable, I use this variational principle for the solution of the forward equation. You can write the solution of the forward equation in this form. So for each sample U, so this little U, let me remind you that it's just the big one, U1, U2, and so on in this sum. For each sample U, we can write the solution of the forward equation in the variational principle as what you see here. So the C, this big C here, that is the set of all the parts from 0, 1 is the domain D, and that is in W1 infinity, such that C0 is the source point and C1 is X. So we can write down the solution of the forward equation in this form. Now it is well known that the solution of the forward equation is Lipschitz, and the Lipschitz constant is not more than the extension 2 for the slowness Sx. U here for each sample U, and there is this little C here, but the C, it only depends on D. It only depends on the domain D. So when you use this variational principle by comparing the minimizing parts for the two samples U and V, we can derive this bound for the difference between the solution of the forward eikonal equation for each point X inside the domain D for two samples U and V. So this is the bound that we have. And you can see that the second term here is finite because both the sequence U and the sequence V belong to this space U. So that is the space of all the little U such that summation here is finite. So this is the difference between the solution of the forward equation for two samples U and V, fixing a point X, and this constant C, it does not depend on X. So for all X inside the domain D, this is what we can show. So from here we can derive the measurability of the forward map G. So that is why the Bayes rule that we have here holds, and we can write the Radon-Nikodym derivative of the posterior with respect to the prior as what we have here. And next we show the well-posedness for the posterior. So we can show this bound for the solution of the forward equation, which leads to the bound for the forward map GU. And using the variational principle for the forward eikonal equation, we can show that for two delta and delta prime, which are not for delta and delta prime such that the Rn norm of them are less than n, we can show that the Hellinger distance between gamma delta and gamma delta prime is bounded by what we have on the right-hand side here. So that means that a little change in delta, it will just lead to a little change in the posterior. So now let me talk about solving the forward equation. When we solve the forward equation, you need to find a way to compute this x, and we can only handle a finite number of terms in this sum. So the first thing that we do is to just take a finite number of k terms in the slowness. So fixing a j, so this is what we defined the truncated slowness function fj, where we just take j terms in this sum. So you see that I just have the summation when the little I here goes from 1 to xj. And then I defined the approximating equation with the slowness sj this way. And we have the source point here, and we also have the Zollner boundary condition. And then we define the forward map Vj in terms of the solution of this equation for the points x1, x2, so on, xn inside the domain D, and the mismatch function phi j is defined in the same way. Now, so here, because we are dealing with finite dimensional probability space, so given this function phi right here, we can always define the probability measure gamma j delta in this way, because here we are just dealing with finite dimension and probability space. So this gamma j delta, it should be a good approximation to the posterior. And we can show that if the sweep norm of the function ci in the slowness, if they are p summable, so that is when summation of all of bi raised to the power p is finite and p is bigger than 1. So bi here we just define it as the L infinity norm of the function ci. We can show it also using the variational form of the solution of the forward equation. We can show that then the Hellinger distance between the posterior gamma delta and the gamma j delta is bounded by what we have on the right-hand side. So this q here is just p minus 1, and here we obviously suppose that p is more than 1. So now let me talk about numerically solving this forward equation with a finite number of terms when I goes from 1 to right here. If you have a sample u, you can obviously compute this summation when I goes from 1 to right. So in this work, we use the fast matching method. So this is the set of points inside the domain D at which we wish to solve for the solution of the forward equation, and we assume that the match size is just this little h. So we need to have a special way to deal with the boundary points, but let me not talk about it here. So this is a sort of point, and this equation, it is just a discrete form of the forward eikonal equation. So what you see is that for each point inside the set at which we want to solve for, we want to find a solution of the forward set. That it is just a set of all the neighbor points for this point. So here on the left-hand side, you see that I have the summation with respect to all the points x beta, which are in neighbor set. Now, so we can show that this equation, it has a solution, and this solution satisfies the lattice condition that you have here. That is, if you have 2 points inside this set, then the difference between the numerical solution at this point and this point is bounded by this right-hand side. So I've got the sweep of the truncated slowness. Okay, so here I've got RD norm of this x alpha minus x beta. So we will use the fast matching method to solve the forward equation. So I'm not talking a lot about the fast matching method here, but I've got a bit here. So that is, we will begin with the source point, and we mark the source point as known. And then we take on the neighbor points of the source point at the triangle point. And then we compute a solution, which I call the T tilde here at all of these triangle points, assuming that the solution at all the neighbor points, which are not known of all of these triangle points, are not less than the solution as the triangle point itself. And then we need to sort. We need to sort the solution tilde at all of these triangle points to find those points as mu for which the solution tilde Jh here is the smallest one. And then the solution of forward equation is Tjh here at this point as mu, which is set as the tilde Jh as mu here. And then it just repeat until it reaches the point at which we want to compute the forward equation. So what you say is that if we use a heap sort, then the cost of solving this forward eikonal equation is just a big O of cardinality of the set points at which we want to solve the forward equation times log of the cardinality of that set. Okay, so actually you see that it is just the set of points at which we want to solve for the forward eikonal equation. And we can also derive the convergence rate for the forward solver. But in order to get the rate for the forward solver, we need to assume that the slowness Fj here belongs to W1 infinity d. So that is the function S star, the F bar, and the Ci here, all of them are in W1 infinity d. So that is here. Right. So S star, S bar, and Ce, all of them are in W1 infinity d. And you assume further that the summation of the W1 infinity of the Ci here is finite, then you can be sure that almost surely the slowness will be in W1 infinity. Now, so the rate of convergence for the fast matching method is big O of h raised to the power 1/2. But then this rate for each sample, it only holds when the mesh size, this actually is less than about. It must be less than this about h0 u. And the Cu here, it also depends on the u. And we can show that the h0 u is of this form. That is e raised to the minus positive c times its sum. And this is the big Cu. So what it means is that if you fix a mesh size on h, there will be some samples u for which this h to the power 1/2 bound here may not hold, because this h0 u here, it can be less than h. But given an h, given a fixed h, we can always use the fast matching method to solve the forward equation. So what it means is that we can always find the numerical solution Jh here. So that is why we can always define the forward map Zh. So it is defined in exactly the same way for the points x1, so on xn inside the domain D. And the mismatch function phi Jh is defined in exactly the same way for each sample u. And because here we are working with just a finite dimensional probability space, So we can define the posterior, the gamma JH delta in terms of the numerical solution for the forward equation. We can define it like here. So if you fix if you fix a mesh size H, you can see that H2 is the minus H2 is the 1/2. Bound it may not hold for some U, because for some samples U is about H0 here will be smaller than H. But we can still show that the Hellinger distance of the gamma J delta and this gamma JH delta. So it's the gamma JH delta is defined here. You can still show that this is less than C times H raised to the power 1/2. So the gamma J delta is the one that we define in terms of the solution of the truncated equation. So the gamma J delta is defined here. So we still have about that is C times H to the power 1/2. And the Hellinger distance between gamma J H delta, which we can find from the numerical solution of the forward equation, and the posterior, it is bounded by this right-hand side here. So in the rest of this talk, let me just talk about using Markov chain Monte Carlo to compute the posterior mean value of quantity of interest. So the quantity of interest, in this case, we just take it as the solution of the forward equation at this fixed point X star inside the domain D. So we just choose H as big O of 2 to the minus L. So we have a hierarchy of resolution levels for the forward equation. So this little L here is 0, 1, 2, and so on. So here we would want to keep this J so that the two terms on the right-hand side here, they are roughly the same. So we just take J as JL. So when you choose JL like here, and you can see that the two terms on the right-hand side are the same. So the Hellinger distance between the approximated posterior, which we can find, and the posterior that we want to find, it is bounded by 2 to the minus L by 2. So here we have a hierarchy of resolution levels for the forward equation, which leads to a hierarchy of approximation for the posterior. And this is the posterior that we wish to find. And this is what we will find. So we will find the posterior of this P at this fixed point X star with respect to the posterior probability for the resolution level, and 2 to the minus big L for the forward equation. So we will use the multi-level Markov chain Monte Carlo. We follow the work that we did before in these two papers here. So the left-hand side is what we want to find. We just write this left-hand side in terms of a telescopic sum. Here you see that I have the difference of the posterior mean of the quantity of interest with respect to two consecutive levels of approximation for the posterior. So I've got this gamma L and this gamma L minus 1 here. So for each term, we still have the solution of the forward equation to solve for. So for each electron L here, we will choose a resolution level and solve the forward equation for this P depending on the electron L. So this is the resolution level for this. So here is the resolution level for this solution of the forward equation that we have. So we will specify what big L prime L is. So this is basically the sum that we will find. So that is the difference of the posterior mean value of this numerical solution of the forward eikonal equation for the resolution level big L prime L. So now we follow. Now we use another telescopic sum for this T big L prime little L here. So we have it as summation, and L prime goes from 0 to big L prime L. Here you see that we have the difference of the numerical solution for the forward equation at two levels of resolution, L prime and L prime minus 1. Now, so let me just remind you that here we have the difference of the posterior mean with respect to the level, the resolution levels L and L minus 1. And here is we have the here we have numerical solution with respect to two resolution level L prime and L prime minus 1. So the Hellinger distance between gamma L and gamma L minus 1 is bounded by the right-hand side. And for the solution of the eikonal equation, well, we have this bound. So this CU here depends on U. And here I've got 2 to the minus L prime by 2. But this only holds if the mesh size is less than this bound H naught U, as you have just seen here. So we only have this bound and this H is less than this H naught U. So we can show that, I don't have time here, but we can show that we can write it in this double telescopic sum as summation of the posterior mean value for some functions of U, for which we can use Markov chain Monte Carlo to compute. So the main point here is that we just need to use a few MCMC samples for those terms for which we solve the forward equation well, and for those terms for which we do not solve the forward equation well, that is we use a fairly big match. Then we need more MCMC samples to compensate for the fact that we don't solve the forward equation well. And because here we work with the Gaussian distribution, so the solution of the forward equation, it is not uniformly bounded for all the samples U. And the mismatch function phi here, it is also not uniformly bounded for each sample U. And if you look at the rate of convergence for the fast matching method, so there's the CU here. You can see that if you fix an H, and the CU here it can still be really big for some U. So that is why we need to modify the method we developed in this paper here for the Gaussian case, which I do not have time for all the details here. This is the resolution level in big L prime little L that we have. So the big L prime little L, that is the one that you see here. So we choose it as the big L minus the little L. And for each term, we use the resolution level L for the forward equation in the posterior, and the resolution L prime for the solution of the forward equation. Then the number of MCMC samples that we choose is this one. To choose the L, the big L minus the sum of the little L plus little L prime. And we can show that in order to get the accuracy level, big O 2 to the minus L by 2. So there is also the polynomial term here, which I don't have here. Oh, yeah, here. So in order to get this resolution level here, the number of floating point operations that we need is just exactly the number of floating point operations that we would need to solve just one sample of the forward equation just to get the same level of accuracy. So that is about the best that we can have. So here what you see is that I've got this 1 by 2q times L here. So that is because when we solve the forward equation, we need to compute the summation of the lay terms in the sum here. So here is the main cost. So if we just have a fixed number of terms, then here we would not have this 1 by 2q here. But then the number of floating point operations that we need by solving the forward equation by the fast matching method with the heap sort, that is just exactly the same as the number of floating point operations that we need to solve just one sample of the forward equation. So that is just the best that we can have. So whatever we do, we cannot get better than just the concept solving one sample of the forward equation. So here you see that there is a polynomial in terms, there is a polynomial factor here. So if we use more samples, then we can reduce this L square. So we can solve the convergence mathematically rigorously. So for the independent sampler, it has been fully solved, and for the PCN sampler, if you assume the spectral gap resultant type similar to the one in this paper here, then you can also show mathematically rigorously the convergence rate for the multi-level MCMC. So now let me finish the talk by a fairly simple numerical example. So we just suppose that we have the forward equation in a two-dimensional domain D, which is a cube of size 1. So the slowness function. So this is a form of it. So we have one random variable U, which follows the normal distribution here. So here we consider the case where this S depends on just one random variable, because in this case we can compute a reference posterior mean for the quantity of interest highly accurately to compare the result of the multi-level MCMC2, but we can fully perform numerical computation for the case where the slowness S depends on many U1, U2, and so on. So the quantity of interest is the solution of the forward equation at this point, 0.5, 0.5. And we compute the reference posterior expectation. It's a small h, so here just take the h as 2 to the minus 12. Okay, so here I use I write here as Gauss-Legendre, but it's not right. We use mid one because we have the Gaussian distribution. So here is the accuracy of the accuracy level of the multi-level MCMC versus the finest resolution level minus L. In the log scale, so you can see that the best fit straight line has the slope 0.5, so on, so that fits into the theoretical convergence rate h to the 1/2 that we have shown. And here we have the CPU time versus the finest resolution level 2 to the minus L. So the red losses that you have here is the theoretical number of floating point operations that we have, and this here are the CPU time that we really need. You can see that the CPU time, it does follow the theoretical number of floating point operations. So I end my talk here. Thank you.